Thank you for introduction. I'm Jie from GraphScope team Alibaba, and it's my pleasure to introduce our project about GART, real-time online graph computation for SQL. Most of data is stored in and updated in the relational databases, and we will face to perform online graph computation while the data is updating. However, perform it on the relational data sets can be quite inefficient. Typically, users have to rewrite graph operations by relational sentences. Moreover, using join operations to express graph operations can be very costly and produce large intermediate results. Let's talk about some requirements of the online graph computations. The first requirement is, of course, the performance. We need the performance of the online graph computation is comparable to specific graph systems. In addition, the results of the graph computation should be fresh. And moreover, we need expressiveness with sufficient graph representation for diverse graph workloads, such as graph traversal or graph algorithms. The first solution to process the online graph computation is to process the data offline. It means this approach needs to combine RDBMS systems with graph systems. First, users need to commit the data on by transactions on RDBMS, and the users need to launch an ETL process to transfer the relational data from RDBMS to graph systems. Once the ETL is done, users can do the graph computation like graph queries on the graph system. This approach can provide good performance and the good expressiveness, while the freshness is very bad because of the time of the ETL. To immerse the graph model and process graph computation online, OLTP systems also support graph processing. Some OLTP systems support graph by the extension, such as a language extension or a storage extension. However, the execution is still inefficient due to the relational operations. Although we have the new standard like SQL PGQ or some graph sentences in some relational databases. A new trend is graph database that store the data as a native graph model, such as Neo4j or Tiger Graph. But these solutions can achieve good freshness of the graph computation, while the transaction performance and the graph expressiveness will be limited because the classic optimizations of RDBMS cannot easily designed on the graph databases, and we need to redesign them on the new type of systems. So our approach is to use the middleware called GART. It is used for real-time online graph computation for the SQL. It bridges RDBMS with graph computation engines such as GraphScope or NetworkX. And the users can submit the OLTP queries or graph computation queries on the specific engines. GART uses logs from data sources to capture data changes. Specifically, there are three main processes. The first one is the pre-process by the system's logs capture and parser. the logs from data sources like bin log in the SQL systems are converted to the log format recognized by GART. We call it transactional logs. And the second is the model transformation, model convert component. We call it RG mapping, means from the relational data sets to the graphical data sets. GART users do not need to rewrite their queries, but they only need to supply convert rules. We call the RG mapping. And I will talk about it in few minutes later. And the third one is dynamic graph storage that it supports efficient simultaneous read and write on the for the graph computation engine, and users can read the graph as the like a multi-version graph. Let's talk about the first component. We capture data changes from data sources by logs. Now we use Debsum for MySQL or PostgreSQL to convert raw bin logs to transaction logs like this JSON format. It has necessary data change information like the before image and the after image. It also have the timestamps to use for the concurrency control and the operations like create or updated. And the model convert component allows users to do not rewrite the requests. We call the traditional requests like SQL ORTB operations or the graph operations called the data manipulation interfaces. And it can be as if on the specific engines. In the GART, we present a new type of interfaces called graph extraction interfaces. Users can define the graph schema by this interfaces to dedicate it what the graph is from and how we can map the relational datasets to graph datasets. And the DBA only defined the data model once if the graph data schema is not changed. Specifically, we can write the RG mapping or the graph extraction interfaces use different formats like CQ, PGQ, YAML, and JSON. This example is the RG mapping written in the CQ, PGQ. In this sentence, we define a graph called LDBC, and we map the label of vertex called person from the relational table called person. And we also defined the properties mapping from the attributes in relational datasets. And it's also like the edges do the same mapping, but the edges also need how the source key and the destination key are mapping in the original relational datasets. And to design an efficient dynamic graph store, we find some key insights about the online computation, graph computations. In a word, we find that we can experience slight freshness trade-offs. It opens design optimization opportunities for the efficient graph, dynamic graph store. And for example, we can use the insight that the required freshness is sufficient for the updating compact struct like CSR. And we also find the computation latencies and the access patterns. for the time reason, the details of the insights I will not talk about in this talk. And we have some optimizations on the graph storage of GART. The first one is we designed the efficient and mutable CSR by segmented edge store that we can update the CSR structure in the segment grid. And we also designed the cross-the-grain MCC and the flexible property storage to release the constraints of the CSR, and it support multi-version operations on the graph storage, and it have comparable performance like the static CSR. Please refer our paper for more details of the graph storage implementations and designs. Next, let's talk about some evaluation of our systems. We conduct experiments on 2 machines, and one for the OLTP server and the other for the graph server. And we extended the standard benchmarks LDBC and TPCC to accommodate the online graph computations. And we compared our performance of the GART use offline approaches and online approaches. And the performance results show that we have comparable OLTP and graphs performance with the offline solution. And the OLTP performance is more higher than the online solution like Neo4j. And the freshness is millisecond level, and it's comparable with the online solutions. Next, I show a simple demo of the GART. This is an RG mapping file of LDBC. And we submit to the GART. And we can update it in RDBMS simultaneously. And the results were changed, and the interfaces of the RDBMS or graph computation is as if on the specific graph engines like NetworkX. So to conclude our talk, we present GART and middleware for real-time online graph computations on SQL. And the key contribution of GART is a transparent data model convention by the RG mapping and an efficient dynamic graph storage with good locality. And you can try the GART on the GitHub, and our code is still ongoing to add more new features. And thank you very much.
Is the GStore component transactional? So when you take the log into GStore, is that a transactionally guaranteed importation?
Yes, it supported snapshot isolation, and the transaction informations are recorded in logs, and we need to reply them as the transactional semantic on the GStore.
On GStore,
Yes.
Okay. And then what's the what determines the frequency of shipping of the log? So you could, you could do that at a transaction level. You could batch it into multiple transactions. Do you have any control over how that works?
Yes. In details, we have designed. We updated the protocol of concurrency control in GART, and the details of the algorithm are presented in our paper. Yes.
Okay.
Yeah. Thank you very much.